Back to pre-calculus. In our last class, we were finishing up, or we were talking about analyzing polynomials algebraically, and we talked about how we could find end behavior, looking at the highest degree in the polynomial and the leading coefficient, whether it's positive or negative, and then we were trying to find zeros. And the first thing we looked at is, can we factor? And that should always be your first option. Can I factor this? Right? And if you can't factor it, what do we do? And that's what we're going to look at today. What happens when we can't factor? Well, if you can't factor and it's a quadratic, you can always use the quadratic formula to find the zeros. Remember, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this polynomial, it's a quadratic, and I know we can't factor, and that's because 2 times negative 4 is negative 8, and then negative 3 goes down here. There are no factors of negative 8 that add to negative 3. Therefore, it is not factorable. So what I need to do is use the quadratic formula. So I get x equals negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. Now from here, a is 2. From here, I have to simplify. I don't really want a decimal at this moment. I want to practice our simplification of radicals. So I have, this is equal to 3 plus or minus the square root. I get 9 minus negative 32. 16, 2, 32. So I get 9 plus 32 over 4. Which ends up simplifying to 3 plus or minus the square root of 41 over 4. So I have 2 real zeros. I have x equals 3 plus square root of 41 over 4, and x equals 3 minus the square root of 41 over 4. Now, if we wanted to put them into decimals, we can go ahead and use our calculator. 3 plus the square root of 41 divided by 4 gives me 2.35 about, and this 3 minus the square root of 41, all of that divided by 4 gives me negative 0.85. And these are my 2 zeros, or my 2 x-intercepts on a graph. So if I can't factor, I can go ahead and use the quadratic formula to find my zeros. And this makes sense. This is a degree 2 polynomial, and I have 2 x-intercepts. So let's go ahead and use and do the next problem. So I'm going to erase this so that I have some space. And again, I can't factor this, so I'm going to go ahead and use the quadratic formula. So I have x equals negative b plus or minus the square root of b squared minus 4ac all over 2. Now when I simplify this, I get negative 2 plus or minus the square root of 4 minus 40 over 2. We have an issue here, because I have 2 plus or minus the square root of negative 36 over 2. When you get a negative value in the radical, right, so it's called the discriminant. If the discriminant is negative, we don't have real solutions. Now, I answered that question before. What do imaginary solutions mean? Well, let's see if we can go back up to the top. So imaginary zeros don't show up on a graph, right? They are not x-intercepts. They're imaginary zeros. That means that the graph does not cross the x-axis. And I asked, can we have one imaginary zero? And the answer is no, we can't, because we had the plus or minus. So in this case, if we kept simplifying, we'd have 2 plus the square root of negative 36 is going to end up being 6i over 2. And we can simplify this even more to be 1 plus 3i. That is one of my zeros. My other zero would be 2 minus 6i over 2, which is 1 minus 3i. These zeros don't show up on a graph, meaning that this function does not cross the x-axis. These are imaginary zeros. This function crossed the x-axis twice. This one does not. So the quadratic formula, there are times where you'll find imaginary zeros, and that means that the function never crosses the x-axis. So let's put this all together. Let's find the end behavior in the x-intercepts, and then we're going to sketch a graph. So let's start with end behavior. So end behavior, EB. Okay, this is a quadratic, so I have a degree 2 polynomial. The leading coefficient is positive, which means as x approaches infinity, f of x must also approach infinity, and as x approaches negative infinity, f of x must also approach infinity, because it must be facing the same direction, something like that. It is a parabola that faces upwards. The zeros, let's find the zeros. The zeros. Okay, to find zeros, we can see if it's factorable. Is it factorable? I believe it is, because factors of negative 21 are 7 and 3. So I'd have x minus 7 and x plus 3 equals 0. So I end up with x is equal to 7 and x is equal to negative 3. I'm going to plot those 2 points right here. Here's negative 3 and here's 7. I have 2 x-intercepts. Okay, now we know the function is going to face, look something like this. It's going to go up this way because the end behavior says it's going to go up that way. And it's going to go up this way because the end behavior says it will go up that way. The question is, how low does it go? Right now, we're not worried too much about what I call the meat of the graph. I'm worried about the x-intercepts and end behavior. But this is a quadratic. So with a quadratic, we could find the vertex. Remember, to find the vertex, we use negative b over 2a. So negative b over 2a is, in this case, 4 over 2, which is 2. So the x value of 2 is the axis of symmetry. All right, this is the x value of the vertex. And we take this x value and we input it into the function. So we're going to find f of 2, which in our function, I'm actually going to input it right into the factored form because it's easier for math-wise. 2 minus 7 and 2 plus 3, which is negative 5 times 5. So I get negative 25, which is a value way down here. So the function is going to come all the way down and up. Okay, and it's not the prettiest of the graphs, but again, this is just a sketch. All right, so we have the end behavior, all right, the end behavior, and we have the x-intercepts. And once we have those two values, we can just sketch a graph, a rough sketch. We could also talk about the y-intercept. The y-intercept of a polynomial is going to be the constant, the only constant in the polynomial. So negative 21. So technically, this graph should cross the y-axis at negative 21. Now again, my graph's a little bit off because it's a rough sketch and the values are so big. But this right here is also the y-intercept. Okay, so we have end behavior, we have x-intercepts, we found the vertex of a quadratic, and we could find the y-intercept, which is the constant of any polynomial. And then we took did a rough sketch. Let's do a couple more. Ooh, this polynomial is already in factored form. Look at this. The question is, what degree is this? What degree polynomial is this? Well, if I was to multiply this out, because I have x to the first and x to the first and x to the first, when I multiply all of this out, I'm going to end up with x to the third and then a bunch of values after that, which means this is a degree 3 polynomial, which means it's an odd degree, and because when I multiply all these x values together, I get a positive 1 in front. It's a degree 3 polynomial with a positive value in front of the highest degree, which means for n behavior, it's going to be as x approaches infinity, f of x will approach infinity, and as x approaches negative infinity, f of x approaches negative infinity. Okay, so again, it's going to look something like this, because this is an odd degree polynomial. Okay, now the zeros, it's already in factored form for us, so they really helped us out here. Right, I could take each of these factors and set them equal to 0. So I have x minus 2 equals 0, I have x plus 3 equals 0, and x plus 3 equals 0. So really, I end up with only 2 zeros. The reason for that, this is a repeated 0. Repeated zeros are very important. Another way to write this function is x minus 2 times x plus 3 squared, which gives me a repeated 0. When I have a repeated 0, that affects how the graph looks. So here's negative 3, and here's positive 2. A repeated 0 is how you get a function to bounce off of the x-axis. So when I'm coming up this way, right? 'Cause I'm starting down here, and as I get closer to the x-axis, I'm gonna hit it, but I'm not gonna go through it. I'm gonna bounce off it and come back down, and that's because it is a repeated 0. If it's not repeated, like 2 is not repeated, I'm going to go directly through 2. But the repeated 0 makes me bounce off. So anytime you see a function that bounces off the x-axis and doesn't go through it, that's because there's a repeated 0 somewhere. Okay. Then it comes down this way, and it goes through the y-axis at negative 18. So it's just going to be way down here somewhere, and that's going to come back up, hit the 2 and go through the 2, and it will look something like this. Okay, again, rough sketch, but what you'll see is the important parts. The end behavior is exactly the way that we said it, right? And I have 2 x-intercepts. One of them is repeated, which is why it bounces off, and one of them is not repeated, so it goes right through that x-intercept. Let's do another one. X cubed plus 8. Again, odd degree polynomial. Leading coefficient, positive. So end behavior is as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x will approach negative infinity. Because it's going to, again, look something like this, because it's an odd degree polynomial with a positive coefficient. The zeros, to find the zeros of this function, I need to factor it. This is a sum of perfect cubes. In order to factor a sum of perfect cubes, I have to use my a plus b times a squared minus ab plus b squared. So in our case, it will be x plus 2, x squared, minus 2x plus 4. Now, I told you that this right here will never, ever, ever be factorable, and it will never, ever, ever give you real zeros. So this thing, not factorable. So in my head, I would say, oh, let's use the quadratic formula. But I know that it's going to give me imaginary answers. Because when I factor a perfect cube, this part always gives me imaginary answers, which means the only zero I have comes from here. And that gives me x equals -2. So the point x equals -2 is my only x-intercept, because this gives me imaginary zeros. So in our case, I have 1 real 0 and 2 imaginary zeros. And the reason I have 2 imaginary zeros is because imaginary zeros always come in pairs. There's no way to have an odd number of imaginary zeros. So I would get 2 imaginary zeros here. If you don't believe me, use the quadratic formula. Go ahead, pause the video and use it and see if it works. Okay, good. So we know it looks something like this, and it goes through the x-axis here, and it goes through the y-axis at 8, because again, the y-intercept is the constant in a polynomial. So it actually goes through the point right here. So when I graph this, it'll come down this way, and it'll go up that way. I'll draw it a little better. Let's fix this. Again, we go through -2 and 8, and I come up and over and up. That's a little better. Looks something like that. Okay, it has a slight curve in here, and it goes back up. And you'll see that if you were to graph it on Desmos, you would see it has that slight curvature and goes through this point at -2 and at 8. Okay. Good. All right. So we are just graphing polynomials by using end behavior and zeros. And of course, if we have a quadratic, we can also use its vertex. Okay, so we're putting it all together. We're no longer using Desmos. Now we're just using Desmos to check our work, to confirm that what we're doing algebraically is actually correct. All right, I'll see you all soon.